fundamental memories. And then as the weeks progress, we're going to go into networks, advanced processors. We're also going to go into advanced memories, hexadecimal arithmetics, instruction sets, instruction set architecture, computer addressing, RISC versus CISC architectures, microprogramming, parallelism, and we might actually have projects. I'm sure in your previous semester, some of you did an Arduino project. So I already know that you have an Arduino project, and most of us have either an Android or Windows machine or device. So we're going to then have one project that we might actually do so that we can have a properly graded semester. And someone says they don't understand. I didn't understand on attendance registration. I need you to be a bit more specific with the question. What didn't you understand? You can switch on your mic and speak. It's quicker that way.
Okay, say I just wanted to know, like, since you said that when we attend the lesson, we have to make sure
I attended the
we
lecture.
mark we mark the register or the attendance. Like we have to be marked in the register. So I didn't understand the instructions of how I can mark the register as you said.
Okay. Have you ever logged onto your Moodle platform?
Yes, I've
When you log into
logged
your
onto
Moodle
my
platform,
module platform.
there's a section called the general section. Can you see that section?
Okay, let me just go to that section now. It is open.
Is my screen visible?
Yes, it's visible.
Yes, sir.
So when you log into your Moodle, this is what you will see. This is what we call the general section, where you have your announcements, your lecture link, and your attendance register. So all you need to do is click on attendance, and there will be a radio button on this section of your points, right? So either you're present, you're late, you're excused, or you're absent. Between 8:30 and 9 o'clock, you mark present. And then you click on Save Changes. Once you click on Save Changes, on my end, this is what I will see. I will see that a specific student has marked the register today, and they've marked themselves as present. So if you mark the register, you're most likely going to appear here.
Thank you, Sam.
Right, moving along. So our assessment is going to be 30% coursework and 70% your final exam. And that 30% may be made up of quizzes, may be made up of tests, may be made up of a different number of assessment criteria as written in section 8.0. Does that make sense? And this criteria is a weighted average, which means that if you get a set of 5 marks, the set of 5 marks is going to be averaged against your 30%. And then you're going to have a final exam that is going to be 5 questions, answer any 4 with a section A that is mandatory. And your primary reading source can be anything in computer architecture. You can get William Stallings' Computer Organization and Architecture, Design Performance, 9th edition or better, or any edition that you get. Or you can download any e-resource that you find online or that you can get from our library. Right. Right. Let us begin. My name is Mr. Paspanojo, as I've said earlier on, and we're now looking at an introduction to computer architecture. And you can also get this resource, which is actually quite good. It's Computer Organization and Architecture by Suruti Ranjan Sarangi. And it was published by McGraw-Hill in 2015. So, one might ask, what is computer architecture? And the basic answer to this is the study of computers. When we're talking about computer architecture, we're talking about the view of a computer as presented to a software designer. Remember, for a computer to work, it needs software. So when we're then creating our software, we need to understand how the computer will function so that we create a software that achieves our intended purpose. So at the end of the day, you will then realize that the architecture of any computer is the view of the computer as presented by a software designer. You need to be in a position where you understand how the computer is logically connected, so that at the end of the day, you then have a fully functional computer that is capable of achieving your intended objectives. If your computer cannot achieve your intended objectives, it has failed in its purpose. It has failed in its purpose because it has failed to do what it is intended to do. And then when we're talking about computer organization, we're saying this is the actual implementation of the hardware. If you look at computer architecture, it focuses on the software, which is the intangible part. And organization focuses on the hardware, which is the tangible part. Combine the two, you then have the basic view of a computer as the one that you're using in front of you right now. You want to be able to understand how the hardware can be implemented within a software design so that it is capable of achieving its intended goals and objectives. So, here are some examples of computers. We have a general desktop computer. We have a portable laptop computer. We have a third generation GSM phone. And we have a personal assistant device. All these are examples of computers. But in the contemporary world, we see there are even greater examples of computers. For example, your television set is a computer. For example, your smartwatch is a computer. For example, the navigation system in your vehicle is a computer. So computers have been infused with our everyday lives, and we need to make sure that whenever we are using these computers, they are achieving their intended tasks. Are we together, ladies and gentlemen?
Yes, sir.
So, in as much as we have familiarization with computers, we also need to familiarize on how computers work. A computer is made up of three major classifications or three major variables or elements. We have the program element. The program element is just a list of instructions that are given to the computer. These list of instructions can come through software installations, they can come through applications, and sometimes you can even hard code the instructions onto the computer so that it achieves what you want it to achieve. For example, when you write queries in databases. And then we have an information store. An information store is just a repository of your data, of your multimedia, or of any piece of logically organized facts that you can use to your advantage. So this can include things such as student reg numbers, getting all these things form what we call our information store. So you realize that with this information store and the program, both are required by the computer in order for it to produce results. So the computer, in essence, then is a logically organized unit that processes an information store according to the instructions that it has been given, and then gives you a result. For example, imagine you have 4,000 videos on your computer, and you want to find a specific video, and that specific video is called video ABC. If you instruct a computer to just output video ABC, are you going to have 3,999 other videos also outputting? This is a question to you. You have 4,000 videos on your computer. You only want to extract one video called ABC. You write a query that says display ABC. How many videos are going to be displayed by the computer?
One video, sir, which is the ABC video.
Right. It will only display one, which is the ABC video. And that ABC video has been instructed by the program to be outputted. If the instructions of the program change, so will the results. So in essence, we can then say any computer requires input, and any computer will process that input that it gets, that it produces an output. Do you understand, ladies and gentlemen?
Yes, sir.
Right. So, for some of us, we've never seen the inside of a computer. And that is how a computer looks like. Basically, any computer that ever existed needs memory. Any computer that has ever existed needs a central processing unit. So you realize that whenever we're talking about computing, whenever we're talking about computers, we're talking about how those fundamental aspects of a computer relate together so that we have something that is usable, so that we have something that is object-oriented or goal-oriented. And we're realizing with the contemporary world that this view of a computer is actually changing. For example, notice how within our graph, within our picture, there's a lot of dead space around components. The silver part that you see is the base of the CPU, and there's nothing on it. So in essence, you need less than an A4 area to have a functional computer. And over time, we've realized that the size of computers is changing. They're becoming small. If you look at your Arduino projects, the small Arduino boards that you're using were examples of computers. And right now on my screen, I'm just trying to show you how modern computers look like. They're small, they allow you to achieve whatever you want to achieve. So you realize that whenever you then buy a computer, you need to look for specific things. You need to look for the memory, you need to look for the processing power, you need to look for the storage. For example, this is what we call a Raspberry Pi computer. It's very small, it's less than, the size is almost similar to a credit card. This part of the computer is the processor, and it works with this other smaller processor. And then these are the basic components. We have your audio, we have your HDMI, we have your different buses to add on other components. We also have our own QSB and VGA components. And if you flip this over on this section, you realize that this MMC card, this memory card represents the hard drive or the secondary store. So that's an example of a modern day computer.
Hello, sir.
Are you still following? Yes, hello. Do you have a question?
Yeah, we cannot see your presentation.
I wasn't presenting anything, but anyhow, I was showing something on my video. Then now you can Google Raspberry Pi, you can Google Arduino, and you will see what we're talking about. Right. Let us move on. So now we're adding two more components to our computer diagram. Remember earlier on, we just had our program, our information store, our computer producing results. Now we're saying we're adding memory, we're adding hard disk. The memory is responsible for storing those programs. It's responsible for storing those programs that instruct the computer on what to do. And that information store is available on your hard disk. We are saying our information store exists on our hard disk because we want that information to exist there permanently. The biggest disadvantage with storing your information store in working memory is that whenever you remove electrical conduct or power to your memory, the memory becomes erased. So we want to avoid the situation whereby our data is erased, our information is erased. In order for us to do that, we need to store our information store on the hard disk. Are we still together?
Yes, sir. Yes,
Do you understand why we need to store information on the hard disk? Is anyone lost so far? All right. Right. So, I'm sure in one of the courses that you took, one of these semesters, you were told about input-output devices, or as they are formally known in most texts, they're known as I/O. And when we're talking about input-output devices, we're talking about the devices that can allow a computer to acquire data. Devices such as your keyboard, such as your mouse. Those are the input devices. And when you look at the output devices, we're saying these are devices that can allow your computer to output data. And this includes your monitor and your printer. So you realize that A full computer system has memory that stores program, which is erasable upon powering off, and a hard drive that stores an information store, which is permanent and cannot be erased even after power off. All these are fed into a computer that processes this information with the aid of input devices such as your keyboard and your mouse, so that it produces an output through your peripheral devices such as your monitors, your printers, your projectors, your speakers, etc. And this is what we call a full computer system. Are we together?
Yes.
Yes, sir.
Yes, sir.
Right. Let's have a discussion. What is the most intelligent computer that you've ever encountered? Or that you've ever used? The most intelligent computer you've ever encountered or used, what is that? Panashi says the brain.
Sir, I want to try.
Yes.
I also wanted to say brain, but it's Farai had already said it.
Right. One of the most intelligent computers that has ever been recorded or created is the brain, with the capability of not only running microprocesses simultaneously, but to also have or understand linguistic meaning. It has the capability to understand linguistic meaning. For example, you can say, if you put on 3 plus 4 kgs onto 7 kgs, how many kgs do you have? And you could have 14 kgs. That calculation comes from just making inference through your brain. So your brain is one of the most intelligent computers that exists out there. You have memories from when you were 5. And these memories include, for example, visually recorded cues or smells or sounds or colors. That laptop or cell phone you're using right now runs out of memory. And eventually you need to start deleting things. So our brains are the most intelligent computers out there. But you realize that when we compare a brain to an electronic brain, which is a computer, there are advantages and disadvantages. For example, if we talk about intelligence, brain is the most intelligent as compared to a computer. If we talk about speed of basic calculations, the brain is somewhat slow, whereas a computer is fast. So you realize that in terms of speed of calculation, a computer is faster than your brain. In terms of throughput, we're saying Your computer never gets tired. As long as it's being fed information, as long as it's being fed enough power, it will always continue to run calculations. Whereas the brain requires a lot of energy in order for it to function continuously without stopping. If we're talking about boredom, for example, a computer doesn't get bored because it's built for one fundamental purpose. And as long as it achieves that fundamental purpose, it will continuously cycle through and repeat the same process over and over, even if the process is monotonous. But the human brain almost always gets bored of doing the same things over and over. Somebody who has raised up their hand with a question. With a question, your hand is up. So, let's look at how we instruct a computer. A computer is instructed by giving it a program, which it then compiles into an executable piece of coding. Then it executes that code to produce an output. For example, we write a program that displays hello world. We put that into the compiler and give it to the computer. The computer creates an executable upon saving the file. And then we take the file onto our desktop, we double click the file to execute it, and the output is going to be hello world. So basically, when we're talking about programs, we use words like we write a program, meaning to say instructions are written down to points and they need to be concise. We use different languages for this, and I'm sure this semester you're doing a programming language such as C. Maybe next semester you'll be doing VB. The semester after that you'll be doing HTML and PHP. The semester after that you'll be doing your C++ and so forth. And then when we're talking about compiling a program, we're saying these programs are written in natural language or are written using some form of syntactic expression. This syntactic expression then needs to be converted into a format that a computer understands. And this is what we call compiling. And a computer understands which language, by the way, if you recall?
Binary language, sir, ones and zeros.
It understands ones and zeros. So when we then tell it to do something, it first needs to convert what we've told it to do into ones and zeros so that it's understandable to the computer. Once it understands what we have told it to do, then it starts executing the program. To the end of the day, you realize that whenever we are instructing a computer, we go through a sequence of processes. We write a program which is compiled and executed, made executable and executed, and produces the output. If either one of these phases fails, it means that at the end of the day, we won't be able to have the output that we wanted the computer to produce in the first place. Does this make sense, ladies and gentlemen?
Yes, sir.
Yeah.
Right. So, remember we said computers are highly intelligent. Again, convert something into binary and then execute it to point. But we also say that computers are somewhat dumb. They can understand natural language to a limited extent. So you realize that most computers can clearly not understand instructions of the form. For example, matrices. Do you remember matrices from our Form 1 mathematics? 0, 1, 0, 1, 1, 0, 1, 0. And we tell it to multiply that. Won't be able to understand. We look at a simple instruction such as find the shortest path between Catholic University and Harare CBD. That instruction is somewhat vague. Instead, it would understand something that goes in the form Catholic University to CBD via Seke Road is 7 kilometers. Catholic University to CBD via Chilemba Road is 5 kilometers. Is 5 greater than 7? That it will understand. But when it comes to natural language processing, we still have lots of problems in that area. So if you want a computer to understand your instructions, you need to be able to write those instructions in a language that makes it easy for the computer to understand. For example, A plus B is equal to C. A times B is equal to C. That is the language that computers understand, and that is the language that makes them capable of processing instructions faster. So you realize that we need to make the instructions simple. You need to make the instructions concise. And computers that use these instructions to process and come up with results are known as instruction set architectures. And instruction set architectures are just instruction expressions that tell you how to write an instruction, what operand to use, what peripheral device connects to what instruction set, etc. So you realize that when we're talking about computers, in most instances, we're talking about the capability to process a set of instructions. And the processor should be able to support the instructions that you write to the computer. If it cannot support those instructions, then the computer will not be able to process anything. So, instruction set architectures can be defined using a number of identifying characteristics. The first characteristic is that an instruction set architecture should be complete, meaning to say it should be able to implement all the programs that the user writes. If a user writes a set of programs and the instruction set cannot implement all the programs, then it is incomplete and will not achieve its objective. Some of the instruction sets you've actually encountered include addition, subtraction, multiplication, division, and or not. For example, data movement or data transfer instructions using your copy, paste, cut, paste, etc. These instructions need to be complete in order for an instruction set architecture to fully function. Second characteristic is that it needs to be concise. When we're talking about conciseness of instruction set architectures, we're saying the instruction set should have a limited size and should not be bulky. Bulky instructions are instructions that exceed a 1000 count limit. In order for a computer to fully function, your instruction sets should range between 32 and 1000 instructions. Anything less than 32 is underutilization. Anything above 1000 is overutilization of your CPU, your processor. So we want to be in a position whereby we understand what exactly we are doing with our processor, and we are using our processor to function optimally. Third characteristic is that any instruction set should be generic in nature. Avoid over-specialization. Generic instructions, for example, are those instructions that you write in your C programming. Int A is equal to 3, int B is equal to 4, sum is equal to A plus B. And writing instruction sets in a generic nature allows for any platform-independent instruction set architecture to also execute these instructions and create an executable. And the key to this is simplicity. Avoid complication. Simplicity is the key to an instruction set architecture that functions optimally. Keep your instructions as simple as possible, but achieving your intended goal. So when we're looking at the designing of an instruction set architecture, we need to answer 3 fundamental questions. How many instructions we have, what they should do, and how complicated should they be? These 3 questions result in the creation of 2 paradigms when it comes to instruction set architecture. We have what are known as RISC-based computers or reduced instruction set computers, and CISC-based computers or CISC complex instruction set computers. The greatest variance between these 2 types of architectures is the instruction set in terms of cumulative count and the complications in terms of executing those instruction sets. So when we're looking at RISC-based machines, we're saying they implement instructions that have a simple and regular structure. And the number of instructions that is implemented range from 64 to 128. And a very good example is your ARM computers, your IBM, your Power PCs, your HP, PA, RISC computers. And then we have the complex instruction set computer, which implements complex instructions that are more highly irregular, allowing it to take multiple operands and implementing complex functionality. It does so by allowing the processing of a large number of instructions at a time, usual instructions that are greater than 500. And an example of this is your Intel-based computers or your fax-based computers. The laptops that you have right now fall in this category. Does anyone have a question? So in summary, we can say up till now, we realize that computers are not as intelligent as they perceive to be, but they are indeed fast. We also realize that instructions are just commands, and the computer billions of instructions per second. Written in a high-level language to basic machine language. We also realize that instruction set architectures are just the semantics of all the instructions supported by the processor. They need to be complete, concise, generic, and simple, which are all fundamental characteristics of an instruction set. By complete, we're saying it needs to have all the parameters endorsed. Concise, we're saying it needs to tell the computer exactly what it needs to do. Generic, we're saying doesn't need to be specialized. And with simplicity, we're saying doesn't need expert knowledge for you to understand the simple instruction, and the computer also understand it. Questions so far? Do we have any questions so far?
See, I have a question.
Okay.
So our programming languages, that is Visual Basic and C programming and C++, transform our language into machine language.
Yes. Remember, there's something called an ASCII value. Have you heard of it?
No, see, I
ASCII
haven't.
is spelled ASCII. And basically, when we're talking about ASCII values, we're saying this is just a standard coding inference for representing anything that you write on a computer. For example, if I write a law on a computer, H has an ASCII value, O has an ASCII value, and these ASCII values are then converted to binary. And when we then convert these ASCIIs to binary, it is the binary that the computer is going to read, not the word hello. Do you understand?
Yes, I understand.
So, for example, the ASCII value of H is 72. What is the binary value of H?
It's 72.
72 is equal to 1001. The question is, how did we get this value?
As for the 72, I just remembered from the chat that we had, I think, last semester. That's when I recalled. But how we got it, I'll have to work on the paper.
So, I sent a message on our class chat. Can you check to see if it's correct?
Right. And then somebody sent in another message, which is equal
No,
to
it's just
001 1001000. And this is the second one. This is the first one. We just put a 1 there, the 2 there. Right. So who is correct and why?
Hello, sir.
Hello?
I think the first one is correct.
Why?
When we want to convert 72 to a binary digit, we create sort of an abacus for binary, let's say ranging from 2 to the power 0 up until we get maybe to 2 to the power 4. Then we look at a number that is closest to 72, that would be 64. So for if we say 64 is closest to 72, we'll put a 1. And then the next number, let me see what that will be, but it's most likely to give us a 0 up until we get to the 2 to the power 0. I
Okay.
can either wait or jump out if it's not clear.
I know how to calculate it. I don't know about your peers.
Say, I think I see the problem there. Can I please correct? I did it up to 2 to the power 9, and then the other person did it up to 2 to the power 6. That is the problem. But then the answer is the same. The abacus thing.
All right. What about the computing fee? How do you calculate it?
Yes, sir. We put a number line going from 1, then we go to 2, all the way to 64. Then we put ones behind the ones that we're going to use in the binary and zeros in the others, which will give us that first binary number.
Are you doing computer arithmetic this semester?
Yes, sir.
Yes, sir.
So can I try?
Yes.
Is someone already talking? Sorry. Can I go ahead?
You can go ahead. Are you going to speak?
Okay. Say I drew an abacus. After I drew an abacus, my abacus has got eight bits, which represent a byte. So I started from the far right end, where I said 2 to the power of 0 to up to 2 to the power of 7. And then I calculated under 2 to the power of 0, I got 1. Then the next one is 2, 4, 8, 16, 32, 64, and 128. After I finished drawing my abacus, I went on to look on the number that we are looking at. It's 72. I looked on the abacus. I said, okay, 72. Which number is close to 72? I saw 64. After I saw 64, I went on the abacus and pointed at 64. And then I saw that 72 has got much weight compared to 64. Since it has got much weight, it means that our transistors are on. Then I put 1 on top. After that, I subtracted 72 minus 64. I got 8. After I got 8, I looked again at my abacus and I went straight on to 8. There is an 8 there without a remainder, a whole number. I went and pointed at 8 and I said, let me compare 8 and 8. It means that it's on because 8 is not bigger or smaller than 8. So it means that the transistor is on. I went on top of the abacus, I wrote 1. Then after that, I said 8 minus 8 is 0. There's no 0 on the abacus. Then from there, I started putting zeros, showing that the transistors are off. So from there, 72, I got answer 0, 1, 0, 0, 1, 0, 0, 0. That's the final answer that I got.
Right. We have abacuses, we have different techniques coming in, we have linear techniques, we have division techniques, and so forth. Right? But at least we're in agreement that 72 converted to binary is 1001 000. Right. So these ones and zeros are what a computer understands. It understands these ones and zeros because computers are built up using what they call logic gates. They build a computer using logic gates. So if something is, for example, firing and something is not firing, then we have a problem. If something is firing and something is firing, then everything is working out fine. So you realize that in the next lecture, when we look at our introduction in detail, we're going to look at some of these logic gates and see how these logic gates compare to, for example, truth tables. And see how these logic gates compare to, for example, decision trees. Understandable? But in essence, computers understand the language of zeros and ones in order for them to process data. And these zeros and ones correspond to our right. So we already talked about the completeness of an instruction set architecture. We talked about, let's talk about something called the Turing machine. So there's an individual called Alan Turing, who is known as the father of computing. So Alan Turing defined intelligence within a computer. He defined intelligence within a computer, and he defined the most intelligent computer that is known, which was somewhat intelligent when tested in the Turing test. His computer was known as the Turing machine, and in simplicity, it was just a tape. A tape had state registers and an action table. The Turing machine had an infinite tape. A tape had state registers and an action table. And when you look at the tape head, we're saying the tape head can move left or right, as denoted by the arrows pointing left and right. And the state register records where the head currently is. The action table gives you the old state and the expected state, as well as the movement, whether it is left or right. Who is lost?
Sir, may you please come again? I didn't quite get that.
The Turing machine was the most intelligent computer that was devised by Alan Turing. A state register that tells us the position of the action table that tells us where the head currently was, where it moved to, and whether the direction was left or right. Say, for example, Right. Can you see the slide menu to the left? The one that
No, sir.
I need you to respond. Can you see the slide menu to the left?
So you can't see your presentation.
Is that a no or yes?
No, sir.
No, sir.
Okay. Right. Can you now see?
No.
Not yet. Now we can see.
You can now see your presentation share.
Right. So currently I'm on slide 21, right? If I move to the left, I go to slide 20. If I move to the right, I go back to slide 21. If I move to the right again, I go to slide 22. So you realize that the Turing machine is almost similar. This head that you see within the diagram has a capability of moving to the left or to the right of the infinite tape. So if we decide to move to this block, nothing has changed because the head is already there. But if we want to move to this new block, it means that the head needs to shift to the left. If it wants to move to this block, it means the head needs to shift to the right. Do you understand?
Yes. Yes, sir.
Right. We then have the state register, registering the state of the head, meaning to say the head position. It has an old position, it has a current position, and it has a new position. And the actions that are going to be taken by the head are written in the action table. So if the head decides to move to the red dot, it means that we have an old state where the head currently is. We have an old symbol that is found within the magnetic tape. And then we have a new state where the head is. That making sense?
No, sir. Please, may you repeat? Hello, sir. Hello, sir.
Yes, hello.
Please, may you repeat that part of the tape head?
Okay. Is the Jamboard visible?
Yes.
Yes, sir.
Right. So, imagine this is our tape head. Our tape head is the numbers A7, 8, 9, 10, 7, and 16. And our tape head is currently at 10. Right. And here we have our action table. Right. So we are saying if we look at our tape head, can either go right or it can go left. Please switch off your mics.
Tutoring machine.
Please switch off your mics.
Oh, sorry.
That is very disturbing. Please let it not happen again. Switch off your mics when you're in the lecture. Right. So this is our head, and we want our head to go or to read the number 16. Head needs to read 16. Which direction is the head going to go?
Right.
Right.
The head is going to go right. To move from 10, 11, then to 16. Do you understand?
Yes, sir. Yes.
Yes, sir.
And we are saying, when we are looking at the head, there is a state register that defines where the head currently is, right? And the head is currently at position 10, which means that our state register is 10, right? Now we go into our action table. What is the old state?
The state was 16. The new state is now 10.
Sorry about that. Network glitch. They were saying our ABCD represents our state. Our 789 represents our values of the table. And my question was, what is the old state and what is the old symbol? Old state is D10. Right. And what then becomes the new state? New symbol.
F16.
The new state cannot be F16. Hence,
It's E11, sir. Because it will go through 11 to get F16.
new state is going to be E11. This becomes your first cycle. The second cycle is going to start at E11. Then move on to F16. And the direction is going to be right and right both cycles. Do you understand? So the action was simply logs in what the head has done. The head has moved here in its first cycle, and then it has moved there in its second cycle. So imagine if this tap was a tap found in a banking institution, and the person deposited $1 into account, so now you have $11 as your balance. And then they deposit $5 into your account, now you have $16 as your balance. But you then decide to spend $80. The head is going to move from this position F16 back to B8, and the direction will be left all the way. As everyone understands. Hello, class, are you there?
Yes, sir.
Yes, we are there.
Did you understand the simple movement of a Turing machine and how all the objects function together?
Yes, sir.
Yes, sir.
Yes, sir.
Let's meet at 2 o'clock to continue this discussion and then look at other items on our introduction. My network is actually getting worse.
Okay, sir.